So I believe I mentioned this last Wednesday, but we have effectively covered all of the new material for your upcoming exam two. Okay. So exam two is only going to consist of questions regarding Thevenin and Norton equivalent circuits, capacitors and inductors as energy storage elements and all of that kind of stuff, and those mathematical relationships that go along with that, and then transient analysis. So for today, we are literally just going to work a single example problem. It is a lengthy-ish one. And then we are going to pivot over to our lab, and we will be officially 100% done with everything for exam number two. On Friday, we're going to start talking about operational amplifiers. Which will be an interesting concept to say the least, because we're going from 2-terminal circuit elements to an 8-terminal circuit element, but we'll cover that when we get there. All right, so the example problem that I want to work with you guys is this in-class assignment, which contains an example wherein we have 2 inductors, okay? So our ultimate goal here is to determine the voltage across our 5-amp current source as a function of time. We're not specifically asked anything about what's going on with the inductors. However, we should know by this point that at a minimum, we need to know what's going on with the inductors at t is equal to 0 minus, that we know what to use in place of the inductor at t is equal to 0 plus for that particular circuit analysis. So, let me ask you guys what I hope is a pretty simple and straightforward question. How are these 2 inductors connected to each other? They are indeed in parallel. So if I have a 1 Henry inductor in parallel with a 3 Henry inductor, what is that equivalent inductance going to look like? So as a reminder, inductors in parallel combine like resistors in parallel. Yeah, so 1 times 3 over 1 plus 3 is just 3 over 4, or 0.75 Henries. So what I'm going to do just real quick like here is I'm going to identify a couple of my nodes, just so I know exactly how and or where I should be connecting that equivalent inductance, right? So my inductors are both connected between this blue node and this green node. So what I'm going to do is essentially I'm going to erase both of those inductors and then replace them with a single equivalent inductance. So I'm erasing both of them, and then I just need to make sure that my equivalent inductance is going to be connected between the blue node and the green node, and I can do that however makes sense to me. So I'm going to choose an inductor here across the diagonal, but as long as it's between the blue node and the green node, you are correct. Okay, so it doesn't matter how you choose to do it, as long as it's between the correct appropriate set of nodes, you're fine. And I'm going to say that this is 3/4 of a Henry, and I'm going to make a simple note here that hopefully this is very obviously the LEQ for this system. Okay, so we've already taken care of that part of step number 4 in our analysis. So from here on out, we can effectively treat this like any other problem. The only thing I also need to pay attention to is what my inductor current is, and I'm going to get to choose the direction for that since it wasn't specified for me. I'm going to choose to say that my reference direction for my inductor current is diagonally down and to the right like this. So this will be IL of t. Okay. So from here, we are just off to the races applying our general technique. Okay. So for step number 1, we need to analyze the circuit at time t is equal to 0 minus. So because it's been a week, I'm going to remind you all that anytime we're at t is equal to 0 minus, we are in a DC steady state condition, which means that our inductor is going to be treated like a short circuit. In this particular circuit, our switch is open before closing, which means that at t is equal to 0 minus, we are going to treat our switch as if it were an open circuit. So now I'm going to just redraw our circuit down here. So we're going to have something akin to this. So here's our 10-volt source. Here's a 4-ohm resistor. Short circuit. Here's one terminal of my open circuited switch. Here's my 4-ohm resistor. 6-ohm resistor. Ohm resistor. My inductor is this short. And then here is my 5-amp current source. And this is the voltage VCS at 0 minus that I'm looking for. And this is the current IL at 0 minus that I'm looking for. So before we get into analyzing this circuit, I hope we can observe something that I believe is pretty straightforward. So because my switch is opened, that 6-ohm resistor and that 12-ohm resistor appear in series. And that series combination of 18 ohms is shorted out by my inductor, which means that the 6-ohm resistor and the 12-ohm resistor will not in any way, shape, or form contribute to what's going on in this particular circuit, right? So just to be clear here, these two guys right here are connected in series. Everybody agree with that sentiment, okay? And then that series combination is in parallel with this short circuit, which means that these guys don't do anything. So I've got a fairly simple circuit for us to analyze now. Does anybody have any thoughts on how I might choose to analyze this circuit? Yes, Matthew. No, because it's going to see 4 ohms of resistance either way. In one case, it's got 4 ohms of resistance in series with a 10-volt source. In the other case, it's just 4 ohms of resistance. So we can't say that all of it's going to flow through the short. Carter.
Post transformation of the 10 volts in order to bring it into amps by the final new current source and the current source.
I don't see anything particularly wrong with that assessment. But I feel like it's more work than we need to do. So we could technically just do mesh here, but again, that's more work than I feel like we need to do. So let me explain my thought process here. Okay. So the voltage drop across the current source is the same thing as the voltage drop across the 4-ohm resistor that's in the middle of the circuit. Okay. So just to be clear, what I'm saying is the positive polarity terminal of the voltage source is at this node, and the negative polarity terminal of this voltage is at this node down here, which is connected by a short circuit to the other side of that 4-ohm resistor, like so. So the voltage drop across the current source is the same thing as the voltage drop across that 4-ohm resistor, and I think that that should be pretty straightforward to figure out. So what I'm going to do, and I know it's been a minute since we've done this, is actually just superposition. Because if we say that the 5 amp source is off, it's very simple voltage division to get the contribution of the 10-volt source to the voltage drop across the 4 ohm resistor, because it's only going to see two 4 ohm resistors in parallel, right? So we would effectively have, let me write it down here. So this is going to be VCS at 0 minus is going to look like 10 volts over 2, because the voltage is going to divide evenly among those two identical resistors. And then when we have the voltage source off and the current source on, our 5 amp source is going to split evenly between those two 4 ohm resistors. So we're going to have our current source's contribution, which is going to be 5 amps over 2 times 4 ohms. So let me just make a note here. This is voltage source contribution, and this is the current source contribution. We could do nodal, we could do mesh, we could do source transformation, we could do any number of those things, but this guy is easy enough to where if we just look at what the circuit looks like with just the voltage source on, it's a simple voltage divider, and what the circuit looks like with the current source on, it's a simple current divider. In each case, they're just split in half. So why make it harder than that if we don't have to, is my question to you all. Okay. Yes, Brendan. I'm sorry, could you speak up? So I did use current division to figure out the current source's contribution. I can't use current division with the 10-volt source on there because the 10-volt source messes up current division. The 4 ohm resistor isn't directly in parallel unless that voltage source is off. So that is exactly how I got my current source's contribution. Okay. So we have 10 over 2, which is 5. And then we have 5 over 2 times 4, which is the same thing as 5 times 2. So that looks like 5 plus 10 is 15 volts. And obviously we would get that exact same result regardless of the method we chose to solve for this particular quantity. Okay. So how would I find IL at 0 minus? Yeah, absolutely right. So all of our inductor current, IL at 0 minus, flows through that 4 ohm resistor. Since we know the voltage drop across the 4 ohm resistor and the resistance of the 4 ohm resistor, it stands to reason that it's just going to be 15 volts over 4 ohms. Which is going to be, let's see. Actually, I guess I could just leave it as 15/4 of an amp because that's fairly simple and straightforward. All right, so before I move on from this step, does anybody have any questions about the analysis that we did here? Right. So very good question. So anytime we are at t is equal to 0 minus, and anytime we're at t is equal to infinity, we are at DC steady state, okay? The switch position literally does not matter. It's those particular times, okay? So we're at the time before the switch changes state. We don't care whether or not the switch is closing or opening or going between two different things. We're at a time before the circuit is in transition. And so that means we're at DC steady state, always, always, always at t is equal to 0 minus. So our inductors are always going to look like short circuits, and any capacitors we have are always going to look like open circuits. At t is equal to infinity, we are a very long time after our switch has changed state. So we are assuming that we have settled back down to a DC steady state condition again, which means at t is equal to infinity, we treat our inductors like short circuits and our capacitors like open circuits. So the switch direction doesn't mean anything about whether we treat our inductors like shorts or anything like that. That's just always at t is equal to 0 minus and always at t is equal to infinity. Any other questions? All right, so now let's analyze our circuit at t is equal to 0 plus. Let me, I guess, give myself another sheet of paper here. You guys could arguably use the back. So for step number 2, we will analyze the circuit at t is equal to 0 plus. So now our switch is closed, okay? So our circuit's going to look something like this. Here is our 10-volt source. Our 4-ohm resistance. Here's our closed circuit for our switch. Six ohms. 12 ohms. 4 ohms. Our 5-amp current source. Here's VCS at 0 plus. What are we going to do with our inductor? You are incorrect. Replace it with a current source because the current through the inductor is the fixed quantity. So here's my current source. Remember that the direction of the current source has to be the same direction as we defined IL. So IL was defined diagonally down and to the right. So our current source is pointing diagonally down and to the right. And then its value will have the exact same value as we had at t is equal to 0 minus, which is 15/4 of an amp. So we can say that IL at 0 plus must be equal to IL at 0 minus is 15/4 of an amp, which is where that current source comes from. And now the only thing that we have left to solve for is that voltage VCS at 0 plus. So anybody have any thoughts on how we might solve for VCS at 0 plus for this particular circuit? Nodal seems like a reasonable thing to do here. There's a lot going on, and because we have our switch is now a closed circuit or a short circuit, that's going to make that superposition approach not really feasible because it's just going to be ugly and gross. Okay. So I'm going to identify my nodes here. Like so. Which node would you guys care to use as the reference node? Bottom, okay? So I'm going to assign this guy a nodal voltage VA, this guy a nodal voltage VB, and this guy a nodal voltage VC. So let's see, we don't have any dependent sources, so we don't have any controlling variable relationships to write. We do have a voltage source, so we're going to have the relationship that 10 volts is equal to VA. And now all we need to do is write our KCL equation at B and our KCL equation at C. So KCL at B is going to look like VB minus VA over 4 ohms minus 5 amps plus VB minus VC over 4 ohms plus VB minus VC over 6 ohms plus VB over 12 ohms is equal to 0. let me just double check some things real quick. So I've got that current flowing to the left, leaving the node. I've got this current flowing down, this current flowing to the right, this current flowing down, this current flowing down. 1, 2, 3, 4, 5 total currents. 1, 2, 3, 4, 5 terms. So because this is an awkward looking node, I just wanted to make sure that I remembered to include all of the different currents that are leaving that node when I wrote my KCL equation. I believe I've got all of them. If you have any questions about how I set up this equation, please don't hesitate to ask. So when we apply KCL at node 2, or excuse me, node C, it's just going to be these three currents right here. So that's going to look like VC minus VB over 4 ohms plus VC minus VB over 6 ohms plus that 15/4 of an amp is equal to 0. And I'm going to now solve this system for those three nodal voltages. Okay. So getting out my trusty TI-36, I'm solving this as a 3x3 system of equations. In my first equation, my coefficient for VA is 1, my coefficient for VB is 0, my coefficient for VC is 0, and my constant term is 10. In my second equation, my coefficient for VA is negative 1 over 4. My coefficient for VB is positive 1 over 4, plus another 1 over 4, plus 1 over 6, plus 1 over 12. And then my coefficient for VC is negative 1 over 4, minus 1 over 6. And my constant term will be positive 5. In my third equation, my coefficient for VA is 0. My coefficient for VB is negative 1 over 4. My coefficient for excuse me, that was negative 1 over 4 minus 1 over 6. Sorry, I got ahead of myself. My coefficient for VC is 1 over 4 plus 1 over 6. And my constant term is going to be negative 15 over 4. And when I solved this system, assuming I did it correctly, I got VA to be 10 volts, VB to be 81 over 8, and VC to be 9 over 8. So before we figure out what VCS is, did anybody else get similar results when they solved that system? You got different results. What did you get? All right. So I honestly believe that I made the mistake here. So let me look at my system again, just real quick. So 1, 0, 0, 10 for my first equation. That seems legit. For VA, I have negative 1 over 4. That's the only VA that I see in that guy right there. For VB, I have 1 over 4 plus another 1 over 4 plus 1 over 6 plus 1 over 12. And then for VC, I have negative 1 over 4 minus 1 over 6. And then positive 5 amps. Okay, I think I found my mistake. Yep. $45 over 4, which is 11.25, and 9 over 4. Yeah. Okay. All right, so which of these three nodal voltages, or which combination of these three nodal voltages, is the voltage VCS that we're interested in? Just VB, right? So VCS at 0 plus is just VB, which is 45 over 4 volts. Does anybody have any questions, comments, or concerns about our analysis for step number 2? All right. So now let's look at step number 3. So we're going to analyze our circuit at t is equal to infinity. So at t is equal to infinity, as I mentioned earlier, our circuit is at DC steady state, which means we're going to simply replace our inductor with a short circuit. So this is the circuit that we should be working with. Here's our 10-volt source, 4-ohm resistor, 4-ohm resistor, 6-ohm resistor, 12-ohm resistor, short my inductance, and here's the quantity VCS and infinity that we're actually looking for. Okay. So Matthew has noticed, for what it's worth, that the 4-ohm resistor, the 6-ohm resistor, and the 12-ohm resistor are all connected in parallel. Let me identify our nodes here really quickly so that I can make sure everybody else is catching that observation. Oops, those guys there should not have been red. So he is indeed correct that those 4 resistors are connected in parallel. So we could notice that we have the 4, the 6, and the 12 between the red and the blue. And we also have our 5-amp current source between the red and the blue. And for what it's worth, let me just make this guy right here, let's say orange or something like that. So I could redraw this circuit and maybe make it a little bit easier to see what's going on. So here's my 10-volt source, my 4-ohm resistor, my 5-amp current source across which I'm trying to find this voltage VCS at infinity. And then over here on the right, I'm going to put the equivalent resistance. So this is 4 in parallel with 6 in parallel with 12. So let me figure out what that is real quick. So that's going to look like a 2-ohm resistor. Correct. So let me just make a little note of that. So that is 4 ohms in parallel with 6 ohms in parallel with 12 ohms. 12 in parallel with 6, I believe, is 4 ohms because 72 over 18 is 4, and then 4 in parallel with 4 is indeed 2. If my mental math is working today. So how could we analyze this circuit?
Would this transformation be overkill?
Again, we could do that, but I feel like it's overkill. I think we can just do KCL. So let me explain what I mean by that, okay? So I'm just going to treat this bottommost node right here kind of as if it's ground. And I'm going to call the voltage here at this node VCS at infinity. It is the only unknown voltage in my system. So if I apply KCL here, I would have VCS at infinity minus 10 volts over 4 ohms minus 5 amps plus VCS at infinity over 2 ohms is equal to 0. And I've got a one equation, one unknown system to solve. So I'm going to use the numerical solver function on my calculator to do just that. So x minus 10 over 4 plus x over 2 is equal to 5. Guess x is equal to 1, just for shits and giggles. Calculator's taking a moment to think about it, and I get VCS at infinity is equal to 10 volts. Yes, sir. So the numerical solver on the TI, so that's second and then the sign button. For those of you that have the Casios, you literally just type in the equation. And then there should be a button to press that literally just says solve. Yeah. If you need any assistance figuring out how to solve a one equation, one unknown system with your calculator, I will definitely help you out with that in just a couple of minutes, but let's wrap up this problem. Okay. So step number 4. Is to, determine the time constant for the circuit. Well, we already figured out at the beginning that LEQ was 3/4 of a Henry because we just had those two inductors, a 1 Henry and a 3 Henry inductor connected in parallel. So we don't need to do that part again, I hope. And now we are going to simply find our equivalent resistance as seen by that inductance, right? So drawing my circuit, so these terminals that I'm drawing right here are where my inductor was. So just to be clear, whenever I'm finding the REQ for my circuit doing transient analysis, I'm taking my equivalent energy storage element out of the circuit. So it doesn't matter if it's a capacitor or an inductor. I'm simply removing it from the circuit, leaving behind an open circuited set of terminals. I'm looking into this set of terminals to find REQ. And this is effectively a Thevenin equivalent resistance, which means I need to be looking at a dead network. So my 5 amp current source is going to be turned off, leaving behind an open circuit, and my 10 volt voltage source is going to be turned off, leaving me with a short circuit. So now I'm simply doing resistor combination to this particular circuit. This looks a little weird and gross to me. So I'm going to identify my nodes and do that process of finding REQ. So here I've got one node. Here is another node. And here is my final node. So I'm going to call that blue node A, the red node B, and the green node C. So putting A on the left-hand side and B on the right-hand side. To go from A to B, I have to go through C. And to go from A to C, I'm going to go through either the 4 or the 6, which means that those two are in parallel. And then to go from C to B, I'm going to go through either the 4 or the 12, which means those two are in parallel. And so I simply have 4 in parallel with 6. So that's going to look like 4 times 6 over 4, excuse me, plus 6. And that is in series with 12 in parallel with 4. 12 times 4 over 12 plus 4. And I wind up getting REQ to be 27/5 of an ohm. From here, my time constant tau is simply LEQ over REQ. So that is 3/4 of a Henry over 27/5 of an ohm. Which I get to be 5/36 of a second. And then the inverse of tau is obviously 36/5 per second. And assuming I don't have any questions about how I determined REQ, we can move on to step number 5, which is just plugging things in to the generic equation. So we could say that VCS as a function of time. So what was the value of VCS at 0 minus? 15 volts. What was VCS at 0 plus? What was VCS at infinity? So I'm going to choose to write that as 40 over 4. E to the negative t over tau, or t times the inverse of tau, is going to look like 36/5 t plus VCS at infinity, which was 10 volts for t greater than or equal to 0 plus. And then simplifying things here, that's going to look like 15 volts for t less than 0 minus, and then 5/4 e to the negative 36/5 t plus 10 volts for t greater than or equal to 0 plus. Alrighty, so that was that in-class assignment problem. You guys have now seen an example where we have multiple energy storage elements that can be combined into a single energy storage element. And then the rest of the process is exactly the same thing that we've been doing.